Hello. So in this lecture, we are going to see the efficiency of Carnot heat engine. So we will derive the efficiency of Carnot heat engine, and we will finally get this result, that is efficiency is equal to, this one is efficiency, which is represented by eta is equal to 1 minus T2 by T1. T2 is the sink temperature, and T1 is source temperature. The temperature which is at higher of these two will be known as source, and the which is having low temperature will be called as sink. Any heat engine to thermal capacity, to we need reservoir, thermal reservoir. One will be source, which is having temperature T1, and another one will be sink. But in between working for working substance, we will be having one. Then down we will be having sink. This is maintained at temperature T2. This is a reservoir, so its temperature won't change. So even if we take heat or we put heat into this reservoir, the temperature will not be changed. That's why thermal capacity of these two, that is source and sinks, will be taken as infinite. So from here, Q1 amount of heat is taken, and this one is here in working substance, we will be taking as ideal gas, working substance. Here we will be taking as ideal gas, and from here work will be done. Some amount of heat will be rejected into the sink Q2. This is the schematic diagram of any heat engine. Here particularly we are going to study about Carnot heat engine. Basically it is made up of four different processes, and it is a cyclic process. So where it has started, it has come back to the same position. So for that, let us draw the indicator diagram, PV indicator diagram here. So we will be taking two isotherms. The two temperatures are there, T1 and T2, two isotherms. So the temperature which is higher will be upper. One isotherm we will take here, and another isotherm will be taken here. This one is T1 and this one is T2. Now we have to draw this Carnot heat engine, the cycle which will be performed. We are going to indicate here. So let us take it started from here, A position, A here. Now this is the first process, which will be isothermal process, and it will go somewhere here. Now let us call this point as P, and this is process number 1. Now after this, there will be an adiabatic expansion. Still volume is increasing, and it will go up to here. So this is the point C where it will touches the next isotherm. Isotherm is the graph which is having same temperature throughout this line. So this dotted line on where temperature will be same. Next step, this is the step number 2. Then again, after this, two steps, step 1, step 2 are expansion. Now we will go for compression. Here compression will be there up to here, up to position D, and then after again compression will be there, but this time it will be adiabatic compression. So this isothermal compression, third one, fourth one is adiabatic compression. So these 4 steps are there. We can name all the steps. AB will be isothermal expansion, and of course, this is a reversible engine, so all the processes will be reversible. So from B to C, it will be adiabatic expansion, adiabatic expansion, and from C to D, it will be isothermal compression, and again the last step, that is this first step, this is second step, this is third step, and fourth step will be from D to A, which will be adiabatic compression. Adiabatic compression. So basically, it is a four-stroke engine because four steps are there in this cycle. So before deriving this result, that is efficiency is equal to 1 minus T2 by T1, we should know that efficiency of any heat engine is given by work done by heat supplied. Work done by the heat engine. So here now work done can be written as work, because in the process heat also will be supplied and heat will be rejected also. Let us write that as minus, because heat coming out of the system will take as minus. So this complete work, you can write this as, because in this cyclic process delta U is 0, so all the work will be delta Q only, and delta Q further can be written as heat supplied plus heat rejected. So by heat supplied. So final relation we got as, for any heat engine, you can write 1 minus of Q rejected by Q supplied. This is the efficiency for any heat engine. Here in this Carnot heat engine, if you see, process 1 is isothermal expansion. So heat, formula of delta Q will be work done, delta Q from first law of thermodynamics, you can write delta Q is equal to delta U plus work done. So for first step we are analyzing. So delta U will be 0 because it's isothermal process. So whatever is work done, same will be delta Q here. Work done in AB, since the volume is increasing, it's positive. That means here heat supplied, since delta Q is positive, so we can tell that the heat will be supplied in this case. So then we can write here that means heat supplied, you can, as we put delta Q in, which is, let us take in A to B, Q1 heat is supplied. B to C, when it is C, delta Q is 0 because there is no heat exchange, because B to C is adiabatic process. Similarly, when you see third step, again you can write delta Q is equal to work done, because delta U is 0. Third step is also isothermal process. In this case, since the volume is decreasing, work done is negative, so delta Q also will be negative. That means heat is rejected in this process. So heat is rejected. Let us call this rejected heat to be Q2. Fourth step, there is no exchange of heat because it is adiabatic compression. So adiabatic process, there won't be any heat exchange. So based on this information, we can further simplify this. Efficiency of Carnot engine is equal to 1 minus heat rejected is in process C to D, and we have called it as Q2, by heat supplied is, which is there in process A to B, efficiency of Carnot engine we simplified to 1 minus Q2 by Q1. So just we need to find out the value of Q1 and Q2. So let us find the value of Q1 here. Q1 you can again, Q1 will be equal to work done in the process first, that is A to B. A to B, from here you can just now we have written delta Q is equal to work done, so because delta U is 0. So work done in isothermal process we know that is N R, the temperature throughout this A to B is T1, so T1 into ln of volume. We will write, final volume is B, so VB by initial volume, that is A, so VA. Similarly for Q2, we are just interested in magnitude. We can write magnitude is nRT2 ln of, here we will be writing, here we are interested in only magnitude because minus sign already we have taken care of, here minus we have already written for negative. So magnitude is always positive. So you have to write the volume VC by VB. Sorry, let us check once again. Above this case, we are writing for this process. This process we are interested in these 2 points. So whose volume is more? C volume is more than D. So we'll write VC by VD here. Because we are interested in magnitude only. Final by initial, if you do, you get minus sign, but already I told you that this minus already we have taken care here. So no need to write minus once again. We will just write the magnitude here. Now when you put this, you will get the efficiency here as 1 minus of Q2, which is nRT2 by ln of VC by VD by nRT1 by ln of VB by VA. This NR and NR is cancelled. So efficiency can be further simplified to be 1 minus of T2 ln of VC minus of VD by T1 ln of VB minus of VA. Now we have to find the relation between these, because this is the extra term which we are getting, and now just after this we will prove that these 2 are equal. That's what we have to prove it. For proving, let us go back to this diagram and we check this. We are going to take the help of adiabatic equation for 2 and 4. 2 and 4, the initial volume is VB and final volume here is VC. For this one, initial volume is VD and final volume is VA. We are going to write the equation, adiabatic equation for it. That means for process B to C, then for process D to A. I'm going to write equation for adiabatic equation. That means for process 2. If you write adiabatic equation for process 2, that means B to C, you can write as PV to the power gamma. Instead of that, we will be using T V to the power gamma minus 1 is equal to constant. This is also one form of adiabatic equation, which is derived from PV to the power gamma is equal to constant. It can be easily derived from this equation. Just you have to write, instead of P, you write nRT by V. And then further simplify, you will get this equation. This is also one form of adiabatic equation only. Now we are applying for BC process. So you can write initial temperature is T1 and initial volume is Vb to the power gamma minus 1 is equal to T2 final temperature into V. T is the final volume to the power gamma minus 1. So from here we have got T1 by T2 is equal to Vc by Vb to the power of gamma minus 1. Let us call this as equation A and let us call this as equation first. We'll be needing those equations later. Now we have applied this for two. Similarly, one more adiabatic process is there, process 4. That means C to A process. Now once again we will apply here, you will get initial, that is T2, and initial is C, Vc to the power gamma minus 1 is equal to final temperature is T1, so V A to the power gamma minus 1. Here initial and final you can check from here. For this process, process number 4, initial will be the direction in which it is going. So initial, then it is going in this direction, this will be final for it. Now further when you write and you find out value of T1 by T2 from here, what we will get? T1 by T2 will be equal to Vc by Va to the power gamma minus 1. Sorry, here the process will not be C to D, process will be D to A. This process will not be, fourth process is D to A, check once again. Fourth process is D to A. This is the D process D. Here we are going from D to A. So fourth is from D to A. So D, so instead of C, we'll write it D here. This one will not be C, this one will be D. So Vd, final Vd, instead of C, wherever C have written, we have to replace it by T, Vd by Va gamma minus 1. This is equation B. Now from first and second A or B, from A and B, we can write LHS is same, that is T1 by T2. So then definitely RHS will be same. So Vd by Va to the power gamma minus 1 will be equal to Vc by Vb to the power gamma minus 1. Further you simplify, you will be getting Vd by Va equal to Vc by Vb. So this is what we got. Now let us check what we have to find B by A. Now let's cross multiply this equation. So Vb by Va, to cross multiply you will get Vb by V, this one multiply here and this case this side, and so you will get Vb by Va is equal to Vc by V, Vc by Vd. Now let us take ln both sides. So ln Vb by Va will be equal to ln Vc by Vd. This is equation 2. Now let us check equation 1 and check this equation 1. In this equation we were getting, in this equation 1 and 2. Equation 1 ln Vc by Vd and ln by ln VB by VD. This will be cancelled out because they are equal. Now you can cancel these two because they are equal from first and second. You can put like this. So from first and second, we can write the efficiency as 1 minus of T2 by T1. This is the final result which we have to derive. Finally we got the efficiency of Carnot cycle as 1 minus of T2 by T1, where T2 is the temperature of sink and T1 is the temperature of source.